Tonight, we're going to talk about the most violent, most luminous, most extreme things in the entire observable universe. Objects so bright, they outshine entire galaxies. Engines so powerful that the numbers describing them stop feeling like numbers and start feeling like mistakes. And here's what's going to change everything you think you know about how the universe is allowed to behave. These things shouldn't exist. Not because they're rare, not because they're hard to find, but because when you actually sit down with the physics, when you follow what has to be happening inside them, the conclusion you keep arriving at is that nothing in the known universe should be capable of producing this much energy. And yet, there they are. By the end of tonight, you're going to understand what a quasar really is, where it comes from, what it's doing to everything around it, and why the fact that it exists at all is one of the most unsettling things we've ever discovered about the cosmos. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year is 1963. Radio telescopes have been picking up strange signals from certain points in the sky for years. Intense, compact signals. Signals that are incredibly strong for how small the source appears to be. Astronomers aren't sure what they're looking at, but they point optical telescopes at these radio sources and try to identify them visually. What they find are points of light. Just points, like stars. So the objects get called quasi-stellar radio sources, eventually shortened to quasars. The name stuck, even though we now know most of them don't actually emit strongly in the radio at all. But here is the thing that shook the field apart. When astronomers took the spectra of these objects, when they broke the light into its component wavelengths to identify what elements were present, they couldn't make sense of what they saw. The spectral lines were in the wrong places, wrong positions, wrong patterns. The light looked like it came from nothing recognizable. Then a Dutch-American astronomer named Maarten Schmidt stared at the spectrum of a quasar called 3C273 for a long time. It was February of 1963. He was sitting with a spectrum he'd been looking at for weeks, and he realized something that changed astronomy permanently. The lines weren't from an unknown element. They weren't alien chemistry. They were hydrogen, just hydrogen, but shifted so far toward the red end of the spectrum that they'd been completely unrecognizable. The redshift was enormous. In astronomy, redshift means distance. When light travels through an expanding universe, the expansion stretches it toward longer, redder wavelengths. The farther the light has traveled, the more it's been stretched. The more it's been stretched, the higher the redshift. And what that redshift told Schmidt about 3C273 was staggering. 3C273 wasn't a nearby strange star. It was approximately 2.4 billion light-years away, and it was bright enough to see with a modest telescope from that distance. That single realization changed everything. Because if something is 2.4 billion light-years away and still bright enough to observe casually, the amount of energy it has to be producing is not a number that fits into any comfortable framework. The implications were so extreme that a significant fraction of the astronomical community initially refused to accept them. Alternatives were proposed. Maybe the redshift wasn't cosmological, meaning it wasn't caused by the expansion of the universe. Maybe it was a local effect, some unusual property of the object itself that was stretching the light without the object actually being far away. Gravitational redshift was proposed. Light climbing out of an extremely strong gravitational field loses energy, and gets redshifted. Maybe these objects were dense, nearby objects emitting redshifted light locally. But the numbers didn't work. A gravitational redshift, as large as observed, would require an object so dense that it would be inside its own Schwarzschild radius, meaning it would have to be a black hole, which raised different, and at the time, equally uncomfortable questions. Every alternative was explored. Every alternative failed. The redshifts were cosmological. Quasars were at cosmological distances. Schmidt published his findings in March of 1963. His paper was a few pages long, one of the shortest, most consequential papers in the history of the field. The response was immediate. Within weeks, Jesse Greenstein and Thomas Matthews confirmed that another quasar, 3C48, had an even larger redshift, even farther away, even more luminous. The floodgates opened. Astronomers began systematically searching for and finding quasars across the sky. Dozens became hundreds. Hundreds became thousands. Eventually, the catalogues would grow to contain millions of confirmed quasars, each one a beacon of almost incomprehensible power from the deep past of the universe, and every single one of them demanding an explanation that physics in 1963 had no clean answer for. The embarrassing truth is that it took years, not because the physics is obscure, but because the answer, when it finally came, required accepting things that were still deeply controversial, things we had to be forced to accept, things the data made us accept whether we wanted to or not. The explanation that astronomers eventually converged on required them to take seriously an object that had itself been considered almost too extreme to be real. Black holes. Not the stellar mass variety that forms when a massive star exhausts its fuel and collapses. Those are real and confirmed, but they start with masses of roughly 5 to perhaps 100 solar masses. What matters for quasars is a completely different category: supermassive black holes. Objects with masses of millions, hundreds of millions, or even tens of billions of solar masses. The first serious theoretical work on what we now call supermassive black holes and their role in powering extreme galactic nuclei came in the 1960s, most notably from the Soviet physicist Yakov Zeldovich and from Edwin Salpeter in the United States, who both independently proposed, in 1964, that accretion onto supermassive black holes could produce the observed luminosities. Donald Lyndon Bell developed the picture further in 1969, making the case that the centers of galaxies, including our own, likely contained massive collapsed objects. But at the time, black holes were still largely theoretical. They emerged from the mathematics of general relativity, from the work of Carl Schwarzschild, who derived his famous solution to Einstein's field equations in 1916, while serving on the Russian front in the First World War. Schwarzschild's solution describes the space-time geometry around a spherically symmetric mass. It contains what we now call the Schwarzschild radius, the critical radius within which not even light can escape. For our Sun, the Schwarzschild radius is about 3 kilometers. Compress the entire mass of the Sun into a sphere 3 kilometers across, and you have a black hole. For decades after Schwarzschild's calculation, most physicists assumed this was a mathematical curiosity. Surely nature wouldn't actually do this. Surely stellar evolution would find ways to avoid it. John Wheeler, the American physicist who actually coined the term black hole in 1967, spent years trying to find physical arguments against their existence before concluding they were real. He then spent the rest of his career enthusiastically exploring their physics. The observational confirmation of black holes as real astrophysical objects took decades. The first strong evidence came from X-ray astronomy in the 1970s with observations of Cygnus X1, an X-ray binary system where a compact object of mass greater than could be a neutron star orbits a massive star. Neutron stars have a mass limit. Above roughly 2 to 3 solar masses, no known nuclear force can halt gravitational collapse. Cygnus X1's compact object was too massive to be a neutron star. It had to be a black hole. The case for supermassive black holes in galactic centers built more slowly. The smoking gun was observations of the motions of stars near the center of our own galaxy. Teams led by Reinhard Genzel at the Max Planck Institute and Andrea Ghez at UCLA began tracking the orbits of individual stars within a fraction of a light year of Sagittarius A in the 1990s. Over decades of observations, they mapped complete orbits. One star, called S2, has an orbital period of about 16 years and passes within 120 astronomical units of Sagittarius A at its closest approach. From the orbital dynamics, the enclosed mass can be calculated precisely. It works out to about 4 million solar masses, concentrated within the orbit of S2. The density, implied by 4 million solar masses within that volume, is so high that no cluster of ordinary objects, no collection of neutron stars or dark matter in any known form could explain it. Only a single massive, compact object fits. A supermassive black hole. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work. The confirmation came definitively in 2019 with the first direct image of a black hole event horizon. The Event Horizon Telescope, a global network of radio telescopes linked through very long baseline interferometry, observed the center of the galaxy, M87. The image showed a bright ring of radiation surrounding a dark central shadow, exactly as predicted by general relativity for a black hole of about 6.5 billion solar masses. The shadow is not the black hole itself. It is the region within which all light paths curve into the event horizon before they can escape. The ring is the photon sphere, where light orbits the black hole before either falling in or escaping outward. In 2022, the Event Horizon Telescope released an image of Sagittarius A itself. The same structure, the same ring, the same dark shadow, confirming what decades of stellar orbit measurements had already strongly indicated. Black holes are not theoretical. They are observed, measured, imaged. They are the most confirmed exotic prediction of general relativity. And understanding them is the prerequisite for understanding what a quasar actually is. A black hole sitting in isolation, undisturbed, is essentially invisible. It curves space-time. It captures anything that wanders across its event horizon. But under ordinary circumstances, it emits almost nothing detectable. It sits in the dark, patient, waiting. What transforms a dormant supermassive black hole into the most luminous object in the universe is the accretion of material. When a galaxy's central region contains significant amounts of gas, dust, and disrupted stellar material, that material is drawn inward by the black hole's gravity. But it doesn't fall straight in. Almost nothing in the universe falls straight into anything, because almost everything is in motion. Almost everything is rotating. Almost everything carries angular momentum. Angular momentum is the quantity that describes how much rotation an object has, and it is conserved. In the absence of external torques, the angular momentum of a system doesn't change. You can redistribute it, transfer it between objects, but you can't make it vanish. This has a critical consequence for infalling material. Gas, with any angular momentum at all, cannot fall straight toward a central mass. It can't. The rotation prevents it. The gas wants to fall in, but its sideways motion keeps carrying it into circular and then elliptical orbits. Instead of a direct plunge, the gas spirals inward. And as more and more material tries to do this from all directions, and as the individual orbits interact and redistribute angular momentum through collisions and magnetic interactions, the net result is a disk. A flattened, rotating structure extending outward from near the black hole. Material that started outside the disk gradually drifts inward as angular momentum is transported outward, until it reaches the innermost stable orbit and then plunges into the black hole. This structure is the accretion disk. And the process of material spiraling inward through the disk, losing gravitational potential energy at each step, is accretion. The energy released by this process, the gravitational potential energy given up as material falls inward through the disk, is where quasar luminosity comes from. And the efficiency of that energy release is the key to everything. Let's be completely explicit about the numbers. Nuclear fusion, the process powering every main sequence star, including our Sun, converts hydrogen into helium. In the dominant chain called the proton-proton chain, 4 hydrogen nuclei are fused into one helium-4 nucleus. The mass of one helium-4 nucleus is less than the combined mass of 4 protons by about 0.7%. That mass difference gets converted into energy according to E equals mc squared. The efficiency of this process is 0.7%. 99.3% of the original mass just becomes helium. Only 0.7% becomes energy. That is the efficiency that powers every star you have ever seen in the night sky. Now, compare that to what happens in an accretion disk. As material spirals inward through the disk, it loses gravitational potential energy. The fraction of rest mass energy that gets converted to radiation depends on how close the innermost stable orbit is to the event horizon. For a non-rotating, or Schwarzschild, black hole, the innermost stable orbit sits at 3 Schwarzschild radii, and the efficiency of mass-to-energy conversion is about 5.7%. For a maximally rotating, or extreme Kerr, black hole, the innermost stable orbit can approach the event horizon itself. The efficiency rises to approximately 42%. 6% minimum, 42% maximum, compared to fusion's 0.7%. This is not a modest improvement. This is an entirely different category of physical process. The least efficient accretion disk around a non-rotating black hole is more than 8 times more efficient than the process that powers every star. The most efficient accretion disk around a maximally spinning black hole is 60 times more efficient. This is why quasars are so luminous. Not because they are using some exotic unknown physics. They are using completely well-understood general relativity and magnetohydrodynamics. The physics is known. The efficiency is real. And when you feed enough material into a system that converts 40% of it into radiation, the resulting luminosity is what we observe in the most powerful quasars. Staggering, unprecedented anywhere else in nature, but physically explicable. That tension is what makes quasars so interesting. The numbers are extreme. The explanation is elegant. The universe turns out to be capable of building these machines naturally, out of gravity, rotation, and gas. No exotic ingredients required. To convey what quasar luminosities actually mean, you need a reference frame. Our Sun emits roughly 3.8 times 10 to the power of 26 watts. That is the power of our star. Every photon of sunlight that has ever warmed a face, every joule of energy that has ever driven photosynthesis, came from that output, sustained over 4.5 billion years. The Milky Way galaxy contains between 200 billion and 400 billion stars. They don't all have the same luminosity. Most are significantly dimmer than the Sun. Some are much brighter. The combined total luminosity of the entire Milky Way, all those stars together, is roughly 20 billion times the luminosity of the Sun. A large galaxy. Not all galaxies are this bright, but this is a reasonable representative figure for a large spiral galaxy. Now, consider the most luminous quasars. The record holder is a quasar designated J05294351, identified using observations from the European Southern Observatory's Very Large Telescope in Chile, combined with archival data from sky surveys. Its luminosity is approximately 500 trillion times the luminosity of the Sun. Let's compare that to our galaxy. The Milky Way is 20 billion solar luminosities. J05294351 is 500 trillion solar luminosities. Divide those. This quasar is about 25,000 times more luminous than our entire galaxy. One compact central region, powered by one black hole, radiating 25,000 times more light than everything in a galaxy of hundreds of billions of stars. If you tried to replace our Sun with this quasar, meaning if you put it at the same distance and turned on that luminosity, the Earth would be bathed in radiation so intense that the concept of the planet as a habitable place would stop being relevant almost immediately. We would not be discussing it. The quasar's fuel consumption is consistent with the output. The central black hole has a mass of roughly 17 billion solar masses. It is consuming approximately 370 solar masses worth of material per year. Not per millennium. Not per million years. Per year. 370 stars the size of our Sun, in mass, falling into this black hole every year. And most of that mass converting to light rather than simply disappearing. When the light from this quasar was emitted, it began a journey of approximately 12 billion years to reach our telescopes. The universe was barely 1.5 billion years old when those photons left their source. Our Sun wouldn't form for another 8 billion years. Earth wouldn't form for another 9 billion years. The atoms in your body hadn't yet been forged in stars. And the quasar was already at full power. Already blazing. Already one of the most luminous things in the universe. Those photons crossed the expanding universe, passed through galaxy clusters that bent their paths, passed through gas clouds that absorbed fractions of them, arrived at Earth, entered a telescope, were dispersed into a spectrum, and confirmed the existence of the most luminous thing we have ever found. That is what 12 billion years of travel looks like when it ends. The anatomy of a quasar is layered, moving outward from the black hole through a series of distinct zones that each contribute to the total observed phenomenon. Starting from the innermost region, Just outside the event horizon of a spinning black hole lies the ergosphere. This is a region of space where the rotation of the black hole drags space-time itself along with it. Frame dragging. The technical name for this is the Lentz-Thirring effect, after Joseph Lentz and Hans Thirring, who predicted it from general relativity in 1918. Inside the ergosphere, space-time is rotating. Anything inside the ergosphere is forced to co-rotate with the black hole, not because of a force in the ordinary sense, but because all paths through space-time inside that region are paths that rotate. There is no path through the ergosphere that doesn't involve rotation in the direction of the black hole's spin. This is a consequence of how curved space-time works. The ergosphere is not inside the event horizon. It is outside it. You can enter the ergosphere and still escape, but you cannot stand still inside it. You cannot remain stationary. The rotation of space-time carries you. The energy stored in this rotation of space-time is one of the primary energy reservoirs tapped by quasar jets. The Blandford-Znaiec mechanism, published in 1977, showed how magnetic fields threading the ergosphere can extract rotational energy from the black hole itself. The rotating space-time winds up magnetic field lines. The magnetic tension in those wound-up fields launches plasma outward along the rotation axis. The energy comes from the rotation of the black hole. As the jet extracts energy, the black hole spins down slightly. The rotational energy of a maximally spinning supermassive black hole is enormous. For a black hole of 1 billion solar masses spinning at close to maximum rate, the extractable rotational energy exceeds 10 to the power of 61 joules. That is not a typo. 10 to the 61 joules. More energy than 1 trillion typical galaxies would emit over their entire lifetime, all stored in the rotation of a single black hole, and accessible through the Blandford-Znaiec mechanism to power jets. This is why the jet power and the disk luminosity of a quasar both scale with the spin of the central black hole. The spin is the reservoir. The accretion disk and the jet are the outlets. Moving outward from the ergosphere and the event horizon, you reach the innermost stable circular orbit. This is the inner edge of the accretion disk. Material inside this radius cannot orbit stably. It plunges inward toward the event horizon without much additional energy release. The location of the innermost stable orbit depends on the spin of the black hole. For a non-rotating black hole, it sits at 6 gravitational radii from the center, where 1 gravitational radius is the Schwarzschild radius divided by 2. For a maximally spinning black hole, the innermost stable orbit can approach 1 gravitational radius from the center. The material at the innermost stable orbit is moving very fast. For a maximally spinning black hole, this material is moving at velocities that are a significant fraction of the speed of light. The disk material at this innermost edge is profoundly relativistic. General relativistic effects are not small corrections here. They are the dominant physics. Moving outward through the disk, the material is still moving at a significant fraction of the speed of light at a few gravitational radii from the center. The orbital velocity drops as the inverse square root of the distance. By the time you're at hundreds of gravitational radii from the black hole, the motion is much slower than light, and classical orbital mechanics becomes a reasonable approximation. But in the innermost disk, special and general relativity are both essential to getting the physics right. The temperature of the disk also varies dramatically with radius. In the innermost regions, temperatures reach tens of millions of degrees. At these temperatures, matter emits primarily in hard X-rays and extreme ultraviolet radiation. The spectral signature of the innermost disk is therefore in wavelengths our eyes can't see, wavelengths that don't even penetrate Earth's atmosphere. Only space-based X-ray telescopes can directly observe the emission from the most energetic inner disk regions. Moving outward through the disk, the temperature drops. A few hundreds of gravitational radii from the center, temperatures are in the range of tens to hundreds of thousands of degrees. Emission shifts into the ultraviolet. At thousands of gravitational radii, temperatures are in the range that produces emission in the optical, the visible light range that our eyes and ground-based telescopes can detect. The combined emission of all these temperature zones, from the innermost X-ray emitting region through the ultraviolet and into the optical, produces a characteristic broad spectral energy distribution. Flat in energy across a wide range of wavelengths, peaking in the far ultraviolet, extending from the radio through the hard X-ray. This spectral shape, often called the Big Blue Bump because of where most of the power comes out, is one of the primary observational signatures used to identify quasars. Above and below the disk, there is a corona, a region of very hot, diffuse plasma, electrons heated to temperatures of hundreds of millions to billions of degrees. The corona is less well understood structurally than the disk. It may be a patchy, irregular cloud above the inner disk. It may form a sandwiching layer. It may concentrate near the base of the jet. Its exact geometry is an active research question. But the corona's observational signature is clear. It produces X-rays through a process called inverse Compton scattering. When an energetic electron collides with a lower energy photon from the disk, the electron transfers energy to the photon, boosting it to higher energy. Photons from the ultraviolet disk get scattered to X-ray energies. The corona is therefore the primary source of the X-ray emission that X-ray telescopes like Chandra, XMM Newton, and NuSTAR observe from AGN. The X-ray variability of quasars is largely driven by variations in the corona. Changes in the corona's properties, possibly magnetic reconnection events or structural fluctuations, produce rapid, large amplitude variations in the X-ray output. Some quasars double in X-ray brightness over hours. That variability constrains the size of the corona. If something varies on a timescale of hours, the emitting region can't be larger than a light hour across. For the most rapidly varying quasars, the corona appears to be extremely compact, just a few to tens of gravitational radii in size. A tiny hot region close to the event horizon of a billion solar mass black hole, radiating more X-rays than entire galaxies. Beyond the disk and corona, moving outward in radius, you reach the broadline region. This is a zone filled with clouds of ionized gas orbiting and moving through the vicinity of the central engine at velocities of thousands to tens of thousands of kilometers per second. The broadline region is not a uniform medium. It's clumpy. Individual clouds, each much smaller than the overall region, orbit in complex paths under the gravitational influence of the black hole. Some clouds are moving toward us. Some are moving away. At any given moment, the full distribution of cloud velocities spans a range of tens of thousands of kilometers per second. When the radiation from the accretion disk passes through these clouds, the clouds absorb it at specific wavelengths and re-emit it. The emission features they produce, The emission lines in the quasar spectrum are spread across a wide range of wavelengths because each cloud contributes at a different Doppler-shifted wavelength. The resulting emission features are broad, full width at half maximum velocities of several thousand to tens of thousands of kilometers per second. This is where the Type 1, Type 2 AGN distinction comes from. In Type 1 AGN, which includes most luminous quasars, you see directly into the broad line region. The broad emission lines are prominent in the spectrum. In Type 2 AGN, the broad line region is hidden behind the torus. You only see the narrow emission lines from the larger scale narrow line region. The reverberation mapping technique has made the broad line region one of the most useful astrophysical tools we have. Here's how it works. The quasar varies in brightness. The accretion disk brightens or dims. That change in ionizing luminosity propagates outward at the speed of light. When it reaches the broad line region clouds, the clouds respond. They become more or less ionized. Their emission brightens or dims accordingly. But there's a time delay. The delay between when the disk changes and when the broad line region responds equals the light travel time from the disk to the broad line region. By measuring this time delay in quasar light curves, you directly measure the radius of the broad line region. Typical broad line region radii for AGN, with luminosities in the range of nearby Seyfert galaxies, are a few to tens of light days. For luminous quasars, the radius scales with luminosity. Brighter quasars have larger broad line regions. The relationship between luminosity and broad line region size is tight enough to be used as a distance indicator. This radius-luminosity relation is a calibration tool for estimating black hole masses across cosmic history. Combined with the velocity of the broad line clouds, measured from the width of the emission lines, you can calculate the mass of the central black hole using basic orbital mechanics. Mass equals velocity squared times radius divided by the gravitational constant. Simple in principle, complex in the systematic uncertainties, but powerful enough that reverberation mapping has provided black hole mass estimates for hundreds of AGN at a range of distances. It is the primary tool for measuring how the black hole mass-galaxy relationship, the M-sigma relation, holds at different cosmic epochs. Whether the correlation between black hole mass and galaxy bulge properties that we see in nearby galaxies also held in the early universe. Whether black holes or their galaxies grew first. These questions are being answered, in large part, by applying reverberation mapping to quasars across cosmic time. Beyond the broad line region, at distances from light months to light years from the central engine, lies the narrow line region. Gas here is moving at velocities of hundreds rather than thousands of kilometers per second. Still fast by everyday standards, but dramatically slower than the broad line clouds. The narrow line region can extend for thousands of light years from the black hole. It spans a significant fraction of the inner galaxy. The narrow emission lines from this region are visible in all AGN, regardless of orientation. The torus doesn't block them. They are the spectral feature that allows astronomers to identify Type 2 AGN, where the disk and broadline region are hidden, and they encode information about the large-scale effects of the quasar on its host galaxy. The gas in the narrow line region is being photoionized by the quasar's radiation. The pattern of ionization, which elements are ionized to what degree, depends on the intensity and spectrum of the ionizing radiation reaching the narrow line region. By modeling these ionization patterns, astronomers can infer the properties of the ionizing source, even when the source itself is hidden. This is particularly valuable for understanding the physical conditions in Type II AGN. The torus hides the disk, but the narrow line region remembers the disk's radiation. It keeps the records. The torus is a key structural component, and it deserves more attention than it typically receives in popular discussions. It's not a sharp-edged donut of uniform material. Modern observational and theoretical work has shown it's a complex, clumpy structure. Think less of a smooth ring and more of a swarm of dense molecular clouds orbiting in a roughly toroidal geometry around the central engine. The torus occupies a range of distances from the central engine, typically from fractions of a light year to tens of light years. It is made largely of gas and dust. The dust component is particularly important because dust is what makes the torus opaque at optical and ultraviolet wavelengths. The exact inner radius of the torus is determined by the dust sublimation temperature. At the inner edge, the intense radiation from the disk heats the dust until it sublimates. Dust can't exist where the radiation is intense enough to heat it above roughly 1500 Kelvin. The inner edge of the torus sits at the dust sublimation radius, where the radiation from the disk has diluted enough that dust can survive. This inner edge moves outward as the quasar luminosity increases. More luminous quasars push the dust sublimation radius farther out. Larger tori. This is one of the observational expectations that has been tested and confirmed. More luminous AGN show evidence for the inner torus edge at larger radii, consistent with the dust sublimation picture. Beyond the dust sublimation radius, the gas column density of the torus determines how opaque it is. High column density tori completely obscure the inner regions for any line of sight through them. Lower column density tori may be only partly opaque. Highly obscured quasars, Type II quasars, are now known to be a significant fraction of the total quasar population. In the early universe, during the peak of quasar activity, a large fraction of the most luminous quasars may have been obscured, their light hidden behind columns of gas and dust, their energy output largely absorbed and re-radiated in the far infrared by the warm dust. Studies of the cosmic X-ray background, the diffuse X-ray glow of the sky produced by the accumulated emission of all AGN throughout the universe, suggest that a large fraction of AGN are obscured. Their X-rays, which can penetrate even thick columns of gas and dust, make it into surveys. Their optical and ultraviolet emission is blocked. The complete census of quasar activity throughout cosmic history requires accounting for these hidden quasars. And accounting for them changes the total energy budget of the quasar era. The amount of energy injected into the universe by quasar activity over cosmic history, when you include the obscured fraction, is larger than simple counting of optically visible quasars suggests. The relativistic jets from quasars are structures that have no real parallel anywhere else in nature. They are beams of magnetized plasma, composed mainly of electrons, positrons, and possibly some protons, expelled from the innermost regions of the accretion system along the rotation axis of the black hole. The velocities involved are extraordinary. Observational measurements of jet plasma speeds, made through very long baseline interferometry, tracking the motion of bright knots within jets, reveal apparent velocities that can exceed the speed of light. Wait, that needs an explanation. Nothing actually moves faster than light. What is observed as superluminal, faster than light, apparent motion is a geometric effect. If a blob of plasma is moving toward you at close to the speed of light, at a small angle to your line of sight, the light it emits when it's farther away arrives only slightly before the light it emits when it's closer. The apparent transverse velocity, how fast it appears to move across the sky, can therefore greatly exceed the speed of light. It's an illusion of perspective, but it's a diagnostic tool. By measuring the apparent superluminal motion, you can constrain the true velocity and the angle to the line of sight. Some jets in quasars are moving at 99.9% of the speed of light, or faster. Plasma accelerated to those velocities. The energy density and particle energies in such a jet are extreme. The electrons and positrons in a relativistic jet are cosmic ray energies. When these high-energy particles spiral through the magnetic field that threads the jet, they radiate. The radiation mechanism is synchrotron radiation. Electrons, spiraling in a magnetic field, emit photons at a characteristic frequency determined by the electron's energy and the magnetic field's strength. Higher energy electrons in stronger magnetic fields emit at higher frequencies. In quasar jets, the magnetic fields are strong and the electrons are energetic enough to produce synchrotron emission across a wide range of frequencies, from radio wavelengths through the optical and sometimes into the X-ray. The radio emission from jets is the primary reason the first quasars were discovered as radio sources. The radio telescopes of the 1950s and early 1960s were detecting the synchrotron emission from quasar jets, not the accretion disk emission. The jets. As radio interferometry improved throughout the 1960s, 70s, and 80s, the jet structures became resolvable. Astronomers could see the elongated, collimated structures extending from the bright central point. They could track the motion of individual knots of emission within the jet over months and years. They could measure the bends, the kinks, the brightening and dimming of different jet regions. Modern, very long baseline interferometry can resolve jet structures at parsec scales in nearby AGN. 1 parsec is about 3.3 light-years. We can see the structure of these jets at scales of light-years, or even less in the nearest examples. The jet in M87, which extends for roughly 5,000 light-years overall, can be resolved in its innermost regions to scales within a few dozen light-years of the nucleus. The Event Horizon Telescope, observations of M87 have resolved the jet base itself at scales approaching the event horizon. These observations show that the jet is launched from very close to the black hole, within a few Schwarzschild radii. This is direct observational evidence for the connection between the black hole and its jet. The energy that powers the jet comes from the immediate vicinity of the event horizon. But the jets don't stop at 5,000 light-years. In the most extreme cases, they extend for distances that dwarf the galaxies that launched them. A giant radio galaxy called Alcyoneus, discovered in 2022, has jet structures and radio lobes spanning roughly 16 million light-years from end to end. That is more than 100 times the diameter of the Milky Way, produced by a single black hole at the center of a single galaxy. And it has since been surpassed. A structure called Porphyrion, identified more recently, spans closer to 23 million light-years. The plasma launched from near an event horizon a few light hours across travels outward until it has crossed a distance that would contain entire clusters of galaxies. What determines the jet power? Multiple factors. The spin of the black hole matters. The amount of magnetic flux threading the event horizon matters. The accretion rate matters. The structure and properties of the accretion disk matter. Some quasars produce powerful jets. Others produce weak jets or no jets detectable by current instruments. The physical differences that cause this variation in jet production are still being worked out. There appears to be a bifurcation in the AGN population. Radio loud AGN, which have powerful jets, versus radio quiet AGN, which don't. Classical optically luminous quasars are mostly radio quiet. About 10% are radio loud. The jet production efficiency varies enormously between these populations. One proposal, called the spin paradigm, suggests that radio loud AGN tend to have more rapidly spinning black holes. The Blandford's-Nyack power scales strongly with spin. A black hole spinning near the maximum rate produces a dramatically more powerful jet than a slowly spinning one of the same mass. If radio-loud quasars have faster spinning black holes, possibly because they grew primarily through mergers rather than through continuous disk accretion, the spin paradigm would explain the radio-loud, radio-quiet distinction. Mergers between two comparably massive black holes can spin up the remnant. The inspiral of two rotating black holes preferentially produces a rapidly spinning merger product. So quasars in systems with recent major mergers would tend to have faster spinning black holes. And faster spinning black holes would tend to produce more powerful jets. The evidence for this picture is suggestive but not conclusive. Measuring black hole spins accurately is technically difficult. The primary method, fitting the X-ray spectrum, and particularly the shape of the iron K-alpha emission line, is subject to modeling uncertainties. But the measurements that exist do show some tendency for radio-loud AGN to have higher measured spins. The jet-spin connection is one of the active research frontiers. The history of quasar activity across cosmic time is one of the most important stories in cosmology. The quasar luminosity function, a measure of how many quasars of each luminosity exist at each cosmic epoch, has been measured in considerable detail across a wide range of redshifts. The picture that emerges is unambiguous. Quasar activity was dramatically more common in the past. At redshifts of 2 to 3, corresponding to cosmic times of roughly 2 to 3 billion years after the Big Bang, the space density of luminous quasars was hundreds of times higher than it is in the universe today. This was the era of peak quasar activity. Cosmic noon. The universe at this time was a more turbulent, more active, more energetically productive place. Galaxy mergers were more frequent because galaxies were closer together in the denser early universe. Cold gas supplies were more abundant. The conditions for feeding supermassive black holes at high rates were more widely available. As cosmic time progressed from this peak, quasar activity declined. Not immediately and uniformly, with some complex redshift dependence. But the trend is clear. By the time the universe was several billion years old, the space density of luminous quasars had fallen by orders of magnitude from the peak. In the universe as it exists today, truly luminous quasars, the kind that outshine galaxies by factors of thousands, are extremely rare. There are some, but they are not a common feature of the universe's current inventory. The universe has entered a quiet phase. The engines have largely wound down. Not because the black holes are gone. They're still there, sitting at the centers of galaxies. 4 million solar masses at the center of the Milky Way. 6.5 billion solar masses at the center of M87. Billions of solar masses in thousands of other galaxies we've identified, but they're not being fed. Their fuel supplies are depleted. The gas that would have fallen in has already fallen in. Or it was expelled by previous episodes of quasar activity. Or it was converted into stars. One way or another, the gas that was available to power quasars at cosmic noon is mostly gone now. The black holes remain. The quasars they once powered don't. We live in the aftermath. The cosmic evening. A quieter, older, more settled universe than the one that existed when quasar activity was at its height. This evolution of the quasar population is directly connected to the evolution of galaxies. Galaxies change over cosmic time. The earliest massive galaxies, formed in the first billion years, were actively forming stars at prodigious rates. Gas was available. Conditions were right for rapid star formation. And simultaneously, their central black holes were accreting and shining as quasars. Over time, as quasar feedback expelled gas and as the available gas supply was depleted, star formation rates declined. The galaxies transitioned from blue and star-forming to red and quenched. The quasars dimmed. The galaxies settled. What we observe in the nearby universe as massive red elliptical galaxies, the giants at the centers of galaxy clusters, are the end products of this process. They were blue and star-forming and had luminous quasar nuclei billions of years ago. They are red and quiescent and have dormant massive black holes now. The quasar era wrote the final chapter of these galaxies' star formation histories. The energy output of past quasar activity shaped them into what they are. The Eddington luminosity is the natural limit that sets the scale of quasar activity. Named for Arthur Eddington, who derived it in the 1920s while working on the theory of stellar structure. The argument is clean. When a luminous source emits photons, those photons carry momentum. As they travel outward and scatter off electrons in the surrounding gas, they push on the gas. Outward, away from the central source. Meanwhile, gravity pulls the gas inward, toward the central source. At low luminosities, gravity easily overcomes radiation pressure. Gas falls in. The disk accretes. The luminosity grows. But as luminosity increases, the outward push of radiation on the gas becomes stronger. At some luminosity, the two forces balance. Radiation pressure pushing out equals gravitational pull pulling in. That balance point is the Eddington luminosity. Above this luminosity, radiation pressure exceeds gravity. Gas gets pushed outward rather than falling inward. The fuel supply cuts off. The luminosity drops back below the Eddington limit. The Eddington luminosity for a one solar mass central object is about 30,000 solar luminosities. It scales linearly with mass. For a black hole of 1 billion solar masses, the Eddington luminosity is about 30 trillion solar luminosities. The most luminous quasars observed are accreting close to their Eddington limits. This connects directly to the black hole mass problem. For J05294351 to have its observed luminosity of 500 trillion solar luminosities, its central black hole must have a mass high enough that the Eddington limit exceeds that luminosity. 500 trillion solar luminosities divided by 30,000 solar luminosities per solar mass gives roughly 17 billion solar masses, which is exactly what the observations indicate. The Eddington argument provides a lower bound on the black hole mass given the observed luminosity. It's not the only way to measure black hole mass, but it's a useful check, and it tells you something interesting. The most luminous quasars necessarily have the most massive black holes. Not by coincidence, by physics. The luminosity ceiling scales with mass. To be brighter, you need a bigger black hole. There are quasars that appear to exceed the Eddington luminosity. Super-Eddington sources. They exist. The simple Eddington argument assumes a spherically symmetric geometry. Real accretion disks are not spherically symmetric. In a disk, radiation can escape more easily perpendicular to the disk plane along the polar directions, while gas continues to flow inward through the disk midplane. The effective Eddington limit for a disk geometry is higher than for spherical geometry. Additionally, at very high accretion rates, the disk inflates. It becomes geometrically thick. A portion of the radiation is trapped within the disk material and advected inward rather than escaping immediately. This reduces the effective radiative efficiency and allows accretion rates above the naively calculated Eddington value. Super-Eddington accretion may be particularly relevant for the growth of the earliest supermassive black holes. If the first seed black holes could sustain super-Eddington growth for extended periods, they could reach billion solar mass scales faster than Eddington-limited growth allows. The compressed growth timescale would help explain the existence of billion solar mass black holes in a universe less than 1 billion years old. The problem of early black hole growth is one of the sharpest tensions between observation and theory in modern astrophysics. The most distant confirmed quasars are found at redshifts above 7. Redshift 7 corresponds to a cosmic age of about 750 million years. The universe was less than 6% of its current age, and yet it already contained quasars powered by black holes of billions of solar masses. The challenge this poses for our models of black hole growth can be stated simply. Black holes grow by accreting. The fastest they can grow, under the Eddington limit, is governed by the salpeter timescale. The salpeter time is approximately 45 million years. That is the time for an Eddington-limited accreting black hole to double in mass for a typical radiative efficiency. If you want to grow from a seed black hole of 100 solar masses to a black hole of 1 billion solar masses, you need to double roughly 23 times. 23 doublings times 45 million years per doubling equals about 1 billion years. The math says you need roughly 1 billion years of continuous Eddington-limited accretion to grow a stellar mass seed into 1 billion solar mass black hole. And we have quasars at redshifts above 7, in a universe less than 750 million years old, already with billion solar mass black holes, already accreting at near Eddington rates. Where is the time? The calculation is right at the edge of being plausible if you assume the most optimistic conditions. Continuous accretion, maximum efficiency, no interruptions. An ideal seed starting as early as possible. Under these ideal conditions, you can just barely fit in the growth. But the universe is not ideal. Real black hole growth is episodic. The simulations show that AGN activity is bursty, not continuous. Gas falls in, triggers a bright phase. The feedback suppresses further accretion. Things quiet down, more gas falls in. Repeat. Each active phase lasts millions of years, separated by longer, quiet periods. If you account for episodic growth rather than continuous accretion, the problem gets significantly harder. And the highest redshift quasars, those above redshift 7, redshift 8, into the first few 100 million years, are the ones that press the constraints most severely. The James Webb Space Telescope has found evidence for AGN activity at redshifts above 10, a universe less than 460 million years old. Some candidate AGN at redshifts approaching 12 or 13, in a universe only a few 100 million years old. If confirmed, these push the growth problem to the point of breaking standard models. There simply is not enough time for stellar mass seeds to grow to the required masses through standard Eddington limited accretion. The solutions proposed by theorists fall into several categories. Direct collapse black holes represent the most popular alternative. These would form in special regions of the very early universe where conditions prevent the normal fragmentation of gas clouds into stars. In most of the universe, gas cools and fragments. A large cloud of gas doesn't collapse as one object. It breaks into many smaller clouds. Each smaller cloud collapses into a star. You get a star cluster, not a massive black hole. But in regions where the normal cooling processes are suppressed, the entire cloud can potentially collapse as a unit. The critical ingredient is a strong ultraviolet radiation field that dissociates molecular hydrogen. Molecular hydrogen is one of the primary coolants that allows gas to fragment on small scales. Remove the molecular hydrogen, and the gas can't cool efficiently enough to fragment. The entire cloud collapses. If the cloud is massive enough, tens of millions of solar masses, the collapse produces a very massive object. This object may become a supermassive star briefly, before collapsing directly into a black hole with a mass comparable to the original cloud. Tens of thousands to hundreds of thousands of solar masses. A seed black hole, vastly more massive than any stellar mass seed. With a massive enough seed, growing to 1 billion solar masses in a few 100 million years is plausible. The conditions required for direct collapse, particularly the ultraviolet radiation environment needed to suppress molecular hydrogen cooling, may have existed in the early universe, in regions near the first luminous sources. This is an active area of theoretical work. The James Webb Space Telescope is providing observational tests. If direct collapse black holes exist, they may be detectable in the very early universe as unusually massive black holes in systems that show no accompanying stellar mass. A black hole sitting in a region without the normal stellar population that should have formed alongside it. Webb's infrared sensitivity at the redshifts of interest is sufficient to potentially detect such signatures. So far, the observations are tantalizing, but not definitive. The early universe is telling us it did something remarkable to build its black holes so fast. We're still deciphering the details. The co-evolution of supermassive black holes and their host galaxies is one of the most important discoveries in astrophysics of the past 3 decades. It wasn't initially expected. Black holes are tiny compared to their host galaxies. The event horizon of 1 billion solar mass black hole has a scale of tens to hundreds of astronomical units. The host galaxy has a scale of tens of thousands of light years. There's a factor of roughly 1 billion in scale between the two. 1 billion. Why should these two objects, separated by a factor of 1 billion in size, know about each other well enough to co-evolve. Why would the mass of the black hole correlate tightly with the velocity dispersion of stars in the galaxy's bulge? Those stars are thousands of light-years away from the black hole. They've never been anywhere near the event horizon. They don't directly feel the black hole's gravity. They're too far away for that. And yet, the correlation exists. Measured. Confirmed. Published repeatedly across many surveys and many methods. The M-sigma relation. Black hole mass proportional to the fourth power of the velocity dispersion. The tightness of this relation across 5 orders of magnitude in black hole mass is remarkable. You can take a galaxy, measure the random velocities of stars in its central bulge, and predict the mass of the central black hole to within a factor of a few, from stars that are nowhere near the black hole. This can only be explained by a co-evolutionary history. The black hole and the galaxy are not independent. They grew together through the same merger history, the same gas accretion history, the same feedback processes. And the dominant mechanism connecting them is the energy output of the quasar phase. When a galaxy has a quasar nucleus, the radiation and winds from that nucleus deposit energy into the surrounding galaxy. The energy carried by quasar radiation is enormous. Even a small fraction of it, if it couples to the gas in the host galaxy, is enough to dramatically alter the galaxy's subsequent evolution. Radiation pressure, direct heating, driving powerful winds that sweep gas out of the galaxy. All of these processes inject the quasar's energy into the surrounding galaxy. If the injection is efficient enough, it can blow out all the gas. Without gas, the galaxy can't form new stars. Star formation stops. The galaxy reddens as its massive short-lived stars burn out and only the longer-lived smaller stars remain. The galaxy transitions from blue to red, from star-forming to quenched. And the quasar, having blown out its own fuel supply, dims. The system reaches a self-regulated equilibrium. The black hole grows until its feedback energy is sufficient to expel the surrounding gas. At that point, the fuel supply is cut off. The quasar shuts down. The growth stops. And the final black hole mass, set by the condition that feedback energy equals the binding energy of the surrounding gas, scales with the velocity dispersion of the bulge. Because the binding energy of the gas in the galaxy scales with the velocity dispersion. This is why the M-sigma relation exists. It's not a coincidence or a mysterious cosmic conspiracy. It's the signature of a physical feedback mechanism. The quasar regulated its own growth. It grew until it produced enough energy to clear its own gas supply. Then it stopped. The final mass is set by that balance. The M-sigma relation is the record of self-regulated quasar feedback in every large galaxy in the universe. Reading the M-sigma relation is reading the history of the quasar era written into the structure of galaxies. The quasar light, traveling through the universe, carries information in its spectrum that goes beyond the properties of the quasar itself. Every intervening gas cloud along the line of sight leaves its fingerprint. The Lyman alpha forest is the most diagnostic of these fingerprints. At 121.6 nanometers, the Lyman alpha transition of hydrogen absorbs radiation passing through neutral hydrogen gas. Each cloud of neutral hydrogen along the line of sight from a distant quasar to Earth imprints a narrow absorption feature at that wavelength in the cloud's rest frame. But because the universe is expanding, each cloud at a different distance absorbs at a different observed wavelength. The forest of absorption features in the quasar spectrum, spanning wavelengths shorter than the quasar's own Lyman alpha emission line, maps the distribution of neutral hydrogen along the line of sight. Dense gas clouds produce deep absorption features. Tenuous gas between filaments produces weaker absorption. Voids in the cosmic web produce transparent regions, windows where the quasar light passes through without being absorbed. By analyzing the statistical properties of this forest across many quasar sightlines, the three-dimensional structure of matter in the universe can be reconstructed. The cosmic web, the network of filaments and sheets and clusters connected by dark matter with vast empty voids between them, is traced by the hydrogen gas, and the gas is mapped by the quasar spectra. The Baryon Oscillation Spectroscopic Survey collected spectra of hundreds of thousands of quasars across the sky, specifically to use the Lyman alpha forest as a three-dimensional map of the universe. From that map, measurements of baryon acoustic oscillations were extracted. Baryon acoustic oscillations are density fluctuations imprinted on matter by sound waves that propagated through the hot plasma of the early universe. Before recombination, the universe was a plasma. Pressure waves, sound waves, propagated through it. When recombination happened, the plasma became neutral gas and the sound waves froze in place. The frozen sound waves left a characteristic scale in the distribution of matter, a preferred separation between overdense regions. About 147 megaparsecs in the universe today. This preferred scale shows up as a peak in the correlation function of galaxy positions and similarly as a feature in the Lyman alpha forest. By measuring the apparent scale of this acoustic peak at different redshifts and comparing to the known physical scale, the expansion history of the universe can be measured, including the effects of dark energy. Quasar spectra have therefore contributed directly to the precise measurement of dark energy, the mysterious component responsible for the accelerating expansion of the universe. The most exotic objects in the universe, used as precision tools to measure the most mysterious component of the universe. The unexpected utility of quasars extends far beyond understanding quasars themselves. The deepest quasar spectra, from objects at the highest redshifts, reveal the reionization epoch in a particularly stark way. At redshifts above about 6, the Lyman alpha forest is no longer a forest. It becomes a trough. The absorption becomes nearly complete. A flat, dark region of essentially zero flux extending blueward of the Lyman alpha emission line of the quasar. This is the Gunn-Peterson trough. James Gunn and Bruce Peterson predicted it theoretically in 1965. They argued that if the intergalactic medium contained any significant fraction of neutral hydrogen, a quasar at sufficient redshift should show nearly complete absorption at wavelengths blueward of Lyman alpha. The intergalactic medium has to be almost completely ionized to be as transparent as it is at low redshifts. Even a tiny neutral fraction of 1 part in 100,000 would produce significant absorption. At redshifts above 6, the trough appears. The intergalactic medium is no longer as transparent. It contains more neutral hydrogen. We are looking into, or through, the reionization epoch. The exact structure of the trough, whether it's uniformly absorbing or shows patchy regions of varying opacity, encodes information about how reionization proceeded. The most straightforward picture of reionization is that the first luminous sources, stars and quasars, each created an ionized bubble around themselves. These bubbles grew as the sources brightened. They overlapped as they grew. Eventually, the bubbles covered the entire intergalactic medium. Reionization was complete. If this picture is correct, the Gunn-Peterson trough should not be completely uniform. It should show variations corresponding to regions that were ionized earlier, near the first sources, versus regions that were ionized later, in the outskirts between sources. And observations of quasars at high redshifts do show this kind of patchy structure. Different sightlines show different amounts of absorption at similar redshifts. Some lines of sight show transparencies, indicating a more highly ionized region. Others show near-complete absorption, indicating more neutral gas. This patchiness is the observational signature of the inside-out reionization process. Bubbles growing and overlapping. The universe being ionized in an irregular, spatially varying way. The discovery of the Gunn-Peterson trough in quasar spectra in 2001 by Robert Becker and colleagues using spectra from the Sloan Digital Sky Survey was a landmark result. It provided the first direct observational evidence for the end of reionization, for the transition between the neutral early universe and the ionized universe we inhabit. And it came from quasar spectra, from those faint, ancient points of light at the edge of the observable universe, doing what they're uniquely able to do, illuminating the cosmic structures that lie between them and us, including the cosmic history written into those structures. When we observe a quasar at high redshift, we are not simply observing an interesting distant object. We are observing the universe at an earlier cosmic epoch. The quasar's host galaxy exists at that epoch. The surrounding intergalactic medium exists at that epoch. The large-scale structure of the universe at that epoch is visible through the quasar's spectrum. The quasar is a time capsule, and the information it encodes, the spectral features, the variability patterns, the absorption signatures, collectively constrain our models of cosmic history in ways that nothing else can. Large spectroscopic surveys of quasars have revolutionized our understanding of the expansion history of the universe. The Dark Energy Survey, the Sloan Digital Sky Survey, and the ongoing Dark Energy Spectroscopic Instrument Survey are using quasars at different redshifts as tracers of the large-scale structure of the universe at different epochs. By measuring how the large-scale clustering of quasars and the baryon acoustic oscillation scale in their distribution evolves with redshift, these surveys constrain the equation of state of dark energy. The equation of state parameter, usually called W, describes whether dark energy is a true cosmological constant, Einstein's lambda, with W equal to -1, or something more dynamic, something that evolves with cosmic time, something that is not simply a property of the vacuum, but a field with its own dynamics. Current measurements from quasar surveys are consistent with W equal to -1. Dark energy appears to be consistent with a cosmological constant. But the precision is not yet sufficient to definitively rule out small deviations. Future surveys, with instruments like the Dark Energy Spectroscopic Instrument, which is currently collecting spectra of tens of millions of galaxies and quasars, will tighten these constraints dramatically. The answer to what dark energy is, one of the deepest questions in physics, will be partly answered by analyzing the distribution of quasars across cosmic time. Computer simulations of galaxy formation have become powerful enough to make detailed predictions about the quasar population. Simulations like Illustris, Eagle, and Illustris TNG model the formation and evolution of large cosmological volumes from the Big Bang to the present. These simulations include gas dynamics, star formation, supernova feedback, and crucially, black hole growth and AGN feedback. The black holes in these simulations start from small seeds. They grow by accreting gas. When they accrete, they release feedback energy into the surrounding gas. The energy from AGN feedback couples to the gas, heats it, and can drive it out of the galaxy. The simulations that include AGN feedback produce galaxy populations that match observations much better than simulations without it. Without AGN feedback, the simulations produce too many massive galaxies, too many large ellipticals, too many bright red galaxies at late cosmic times. With AGN feedback, the massive end of the galaxy population is suppressed. The simulations produce the right number of very massive galaxies, and those massive galaxies tend to have quenched star formation histories, as observed. This is not a trivial result. The simulations use AGN feedback prescriptions that are necessarily simplified. The actual physics of how quasar energy couples to galaxy-scale gas is not perfectly understood. The simulations implement schematic models, and yet they work. The success of AGN feedback in making galaxy formation simulations match observations is one of the strongest independent lines of evidence that the co-evolution picture is correct. Quasar feedback is not a theoretical hypothesis. It is a required ingredient in our best models of how the universe formed the galaxies we observe. One of the most unexpected phenomena in recent quasar research is the discovery of changing look AGN. These are objects that transition between different spectral types over timescales of months to years. A Type 1 AGN, showing the broad emission lines of the directly visible broad line region, can transform into a Type 2 AGN, with the broad lines absent, in a matter of years, and then transform back. The standard unification model says that Type 1 and Type 2 AGN are the same type of object viewed at different angles. The torus either blocks your view of the broadline region, or it doesn't, depending on orientation. But orientation doesn't change on timescales of years. The torus is a structure of light years in size. Moving it out of the line of sight in a matter of years would require velocities far exceeding what is physically plausible. So changing look AGN can't be explained by orientation changes. Something else is happening. The most natural explanation is that the accretion rate of the central disk is changing dramatically. When the accretion rate is high, the disk is luminous. The ionizing radiation is intense. The broadline region is highly ionized and producing prominent broad emission lines. Type 1. When the accretion rate drops dramatically, the disk becomes much fainter. The ionizing flux drops. The broadline region clouds are no longer sufficiently ionized. Their emission fades. The broad lines disappear or become very faint. The object appears as a Type 2 or intermediate type. Then the accretion rate recovers. The disk brightens. The broadline region re-ionizes. The broad lines return. Back to Type 1. This scenario requires that accretion rates can change by large factors over timescales of years to decades. That's relatively fast. Accretion disk instabilities can certainly produce rapid changes. Thermal instabilities, radiation pressure instabilities, changes in the rate of gas supply from the host galaxy. tidal disruption events, where a star strays too close to the black hole and gets shredded, providing a sudden burst of fuel. All of these can produce dramatic accretion rate changes on the relevant timescales. The study of changing look AGN is a relatively young field, accelerated by the availability of large-scale time domain surveys that monitor millions of sources repeatedly over years. Surveys like the Sloan Digital Sky Survey, the Zwicky Transient Facility, and others have identified hundreds of changing look AGN by comparing spectra taken years apart. The phenomenon appears to be more common than initially expected. Large fractions of the AGN population may show some degree of changing look behavior over decade timescales. This has implications for our understanding of the quasar population as a whole. If quasar activity is strongly variable, if individual objects can turn on and off dramatically over timescales much shorter than typical AGN survey cadences, then the number of quasars we observe at any given time may significantly undercount the total number of objects that are actively accreting in some sense. Objects currently in a dim state wouldn't be classified as quasars, even though they have recently been, and may soon be again, among the most luminous objects in the universe. The duty cycle of quasar activity, the fraction of time that a galaxy's black hole is in an active quasar-like state versus a quiet state, is an important number for understanding the overall energy budget of black hole accretion over cosmic history. Changing look AGN are windows into this duty cycle. They are showing us the switching behavior of accretion disks in real time. The switches from high to low and back again. The mechanism driving those switches. The conditions under which a disk can transition between dramatically different accretion rate regimes. Understanding the duty cycle is understanding how much total energy quasars have deposited into the universe over all of cosmic history. And that total energy budget directly connects to the growth of the universe's entire supermassive black hole population. Every solar mass of black hole that exists today, every gram of it, was accreted at some point. And the accretion event that grew it released radiation. The total energy released by all those accretion events, integrated over all black holes and all of cosmic history, is enormous. The Salton argument, proposed by Andrei Salton in 1982, uses the observed quasar luminosity function and the efficiency of accretion to calculate the total mass that should have been accreted by all supermassive black holes by the present day. This predicted total accreted mass can be compared with observations of the local supermassive black hole mass function, the total mass of supermassive black holes in the universe today. The two independently derived numbers are in reasonable agreement. This is a powerful consistency check. The quasars we observed in the past are indeed the events responsible for growing the black holes we observe in the present. The energetic past connects directly to the quiescent present. The future of quasar research is going to be transformed by gravitational wave astronomy. This is not a speculative statement. The infrastructure is being built. The first generation of detectors has already made the foundational discoveries. LIGO and Virgo detect gravitational waves in the frequency range from about 10 to a few thousand hertz. In this band, the signals come from merging stellar mass black holes and neutron stars, objects with masses of a few to a few hundred solar masses. These detections, hundreds of them now, have confirmed that binary compact objects merge throughout the universe, tested general relativity in strong field conditions, and measured the Hubble constant through gravitational wave standard sirens. But supermassive black holes don't produce gravitational waves in this frequency range. Their mergers happen at much lower frequencies: millihertz, microhertz, nanohertz. At these frequencies, detecting gravitational waves requires detectors with much larger baselines. Pulsar timing arrays are already making progress at the nanohertz end. A pulsar timing array uses a network of millisecond pulsars, neutron stars spinning hundreds of times per second with extraordinary rotational stability, as reference clocks. Gravitational waves passing through the galaxy slightly change the distances between the pulsars and Earth, causing minute but correlated variations in the arrival times of pulsar pulses. By monitoring dozens of millisecond pulsars over years and decades, these arrays are sensitive to gravitational waves, with periods of years corresponding to the nanohertz frequency range. In 2023, multiple international collaborations announced the detection of a stochastic gravitational wave background in the nanohertz band. A diffuse hum of gravitational waves coming from all directions simultaneously. The signal is consistent with what would be expected from the ensemble of millions of supermassive black hole binary systems throughout the universe, all slowly spiraling together and radiating gravitational waves. This is not a detection of any individual system. It is the gravitational wave static produced by the entire population of merging supermassive black holes integrated over cosmic history. And the measured properties of this background are broadly consistent with the predictions from our understanding of the quasar population and the merger history of galaxies. The quasars we observed in the electromagnetic spectrum predicted a certain level of gravitational wave background. And the gravitational wave detectors are seeing something consistent with that prediction. The two entirely independent windows on the universe's history are beginning to see the same story. At millihertz frequencies, the laser interferometer space antenna will provide the next leap. 3 spacecraft in a triangular formation, 2.5 million kilometers apart, connected by laser beams. The scale of this baseline gives sensitivity to the gravitational waves from merging supermassive black holes throughout most of the observable universe. When 2 galaxies merge, their central black holes eventually come together. The final stages of a supermassive binary, the last parsec of inspiral before merger, will produce a gravitational wave signal detectable by LISA from anywhere in the observable universe. LISA is expected to detect hundreds to thousands of such events per year, depending on the rate of galaxy mergers and the properties of the black hole binary population. These detections will be transformative. Masses and spins of merging black holes, measured with exceptional precision. The mass ratio of the merging pair. The distance from the gravitational wave amplitude. The sky position from the combined signal of the 3 spacecraft array. All of these parameters, for every detected merger, will build a detailed census of supermassive black hole mergers across cosmic time. Combined with electromagnetic observations of the host galaxies, the information will provide an unprecedented view of how galaxies grow through mergers and how their central black holes co-evolve. LISA will also detect gravitational waves from extreme mass ratio inspirals. These are systems where a stellar mass compact object, a black hole or neutron star, spirals into a supermassive black hole. These systems produce gravitational waves for years before the final plunge, encoding detailed information about the space-time structure around the massive black hole. They will provide some of the most precise tests of general relativity in the strong field regime, essentially mapping the space-time geometry around a supermassive black hole by tracking the gravitational waves emitted by an object spiraling through that geometry. All of this is coming. The instruments are being built. The algorithms for detecting and analyzing the signals are being developed. The science cases are being refined. Within a decade, gravitational wave astronomy of supermassive black holes will be a reality. And the picture of the Quasar era, of the black hole growth history, of the connection between galaxy mergers and AGN activity will be tested and refined with a completely new class of observations. There is a sentence that appears in the abstracts of dozens of papers published since the James Webb Space Telescope began returning data. The sentence, in various forms, says something like, "This discovery is difficult to explain with standard models of black hole growth." It appears a lot. James Webb was designed to see farther than any telescope before it, into the epoch when the first stars and galaxies were forming, into the first few 100 million years after the Big Bang. What it found there surprised a significant fraction of the people who built it. Not because it found nothing, because it found too much. The first galaxies are larger, more structured, and more massive than models predicted for that epoch. And they have active galactic nuclei, at redshifts above 10, corresponding to cosmic ages of less than 450 million years. James Webb has identified objects with the spectral signatures of accreting black holes. Some of them are significantly overmassive relative to their host galaxies. In the nearby universe, there's a tight ratio between black hole mass and galaxy stellar mass. The black hole is typically about a few thousandths of the total mass of the galaxy's stars. The M-sigma relation, which tracks black hole mass against galaxy bulge velocity dispersion, encodes a similar co-regulation. But in the early universe, as revealed by James Webb, some of the identified black holes appear far too massive for their host galaxies. The black hole has grown faster than the galaxy, or the galaxy hasn't finished growing, or the co-regulation mechanisms that produce the tight ratios we observe in the nearby universe hadn't yet had time to operate. Which one is it? Isn't fully clear yet. The data is recent. The debate is ongoing. But the implication is that the relationship between black holes and their host galaxies may have a different character in the early universe than it does today. The co-evolution we see in the nearby universe, the tight M-sigma relation, the co-regulation through feedback, may be the end state of a process that begins with the black holes running somewhat ahead of their galaxies, getting their mass established first, and then regulating the galaxy's growth, rather than the black hole and galaxy growing in perfect lockstep from the beginning. This would have implications for the direction of causality in the co-evolution story. Does the galaxy set the conditions that allow the black hole to grow? Or does the black hole grow rapidly, and its feedback then shapes the galaxy? The early universe data from James Webb is providing a way to test this. And the early indications suggest the black hole gets there first, then writes the rules. There's also the question of what these early black holes are. Where did they come from? The most natural seed for a supermassive black hole is a stellar mass black hole left over from the death of a massive star. A star of perhaps 100 to several hundred solar masses, exhausting its nuclear fuel, collapsing. A black hole of tens to perhaps hundreds of solar masses forms. This is the straightforward seed. But getting from tens of solar masses to billions of solar masses in less than 500 million years, even with continuous Eddington limited accretion, is impossible by a comfortable margin. The salpeter time of 45 million years means that even starting at 100 solar masses and accreting at the Eddington limit without interruption, you reach 1 billion solar masses after roughly 23 Salpeter times. 23 times 45 million years is more than 1 billion years. But the universe was only 450 million years old at redshift 10. The math doesn't work. The stellar mass seed scenario can't produce billion solar mass black holes at redshift 10. Even with super Eddington accretion, stretching the numbers gets difficult. So, what else? Direct collapse black holes are the leading alternative. The idea is that under certain conditions in the early universe, massive clouds of pristine gas that has never formed stars and has not been enriched with heavy elements, can collapse directly to form black holes of thousands to hundreds of thousands of solar masses, without going through a stellar phase. The key condition is that the gas has to be prevented from fragmenting into stars as it collapses. If the gas can cool efficiently, it fragments. Pieces of it collapse to form stars. The collapse of the overall cloud is halted. But if the cooling is suppressed, if the gas is exposed to a strong radiation field that photodissociates the hydrogen molecules that normally allow efficient cooling, the cloud can't fragment. It stays together. It collapses as a whole to a much more massive object. And that more massive object can collapse directly to a black hole of thousands to hundreds of thousands of solar masses. A massive seed, one that has a much shorter path to billion solar mass scales. From 100,000 solar masses, Eddington limited accretion can reach 1 billion solar masses in roughly 7 Salpeter times, 300 million years, which could fit comfortably before redshift 10 if the seed formed early enough. Direct collapse black holes haven't been definitively detected. They're predicted to produce specific electromagnetic signatures that differ from ordinary star-forming regions. James Webb has been searching for them. Several candidate objects have been identified. None confirmed conclusively yet. But the search is active, and the stakes are significant. If direct collapse black holes are real and common, they solve the seed problem for early supermassive black holes. If they're rare, or don't exist in the numbers required, we need something else. Some other mechanism that hasn't been fully theorized yet. The possibility that something else entirely is going on, something outside our current models, is uncomfortable but not dismissible. The James Webb data is young. The tension it's creating between observation and theory is real. And the resolution may require extending or modifying our understanding of how black holes formed and grew in the first billion years. These are open questions, not rhetorical open questions. Genuinely unresolved questions that papers are being published on right now, in this year, in this decade. The Quasar story isn't finished. The chapters on the earliest black holes, the formation of the first seeds, the nature of the coevolution between black holes and their galaxies at the very earliest epochs, are actively being written. By telescopes in space. By computers running models at major research institutions. By graduate students staying up late with data they don't fully understand yet. This is one of the things that makes astronomy different from most human endeavors. The objects we're studying are so old, so distant, so extreme, that every new observation has a real chance of changing something fundamental about how we understand the universe. Not adjusting a coefficient in a model, actually changing the picture. The James Webb Space Telescope, in its first few years of operation, has already produced several results that required revising expectations rather than simply confirming them. The early universe looks different from what we expected. The black holes at the centers of early galaxies are more massive, arrived faster, and behave differently than standard models predicted. What the next decade of observations will reveal is genuinely unknown, and that's not a comfortable position. Scientists prefer models that work, but it's an honest position. And it means that the questions we've been asking about quasars, about what they are, where they come from, how they shape the universe, are not fully answered. We understand the nearby ones reasonably well. The physics of accretion, the structure of the disk, the anatomy of the jets, the feedback mechanisms, the co-evolution with host galaxies. All of that is well established by decades of observation and theory. But the earliest ones, the objects that were active when the universe was less than 1 billion years old, are still surprising us, still producing data that challenges us to think more carefully, still being extreme in ways that our models have to work to accommodate. That's quasars. Even in the era of the James Webb Space Telescope, they're not done being difficult. There is something that sits underneath all of this physics, underneath all the numbers and mechanisms and observations, that is worth naming clearly. The universe did not have to work this way. That statement needs unpacking. What does it mean for the universe to not have had to work a particular way? We don't know if the laws of physics could have been different. We don't know if other universes with different physical constants are possible. These are philosophical questions that physics can't fully answer. But within our universe, with the physical constants we have, the efficiency of gravitational energy extraction around a rotating black hole is set by the geometry of general relativity. It happens to be high, remarkably high, between 6 and 42%. Compare this to what it could have been. If black holes were less efficient accretors, the luminosities of quasars would be much lower. If the innermost stable orbit were farther from the event horizon, less energy would be released. If the ergosphere was smaller, less rotational energy would be available. The universe's physics could plausibly produce a universe with accreting black holes that are much less luminous. But it doesn't. The physics that describes space-time curvature and the physics of matter orbiting near the maximum curvature happens to produce very efficient energy conversion. And the universe produces supermassive black holes. And it produces them in large numbers, at the centers of virtually every large galaxy. And those black holes get surrounded by gas in the natural course of galaxy formation and evolution. And that gas falls in. And the result is objects that can outshine every star in an entire galaxy by factors of up to 100,000. None of this required exotic physics. None of it required special initial conditions fine-tuned to produce extreme objects. It all follows from the general physical laws and the straightforward dynamics of galaxy formation. The universe, given its physical constants and the standard process of structure formation from quantum fluctuations in the inflationary epoch, naturally produces the most luminous things that exist. That is remarkable. It means that extreme luminosity, the most concentrated radiative power in the universe, is not a rare exception. It's a standard product of ordinary gravitational physics applied to the right size scales. Quasars are not aberrations. They are the universe doing what gravity does when enough matter accumulates in one place. A natural consequence of the same physics that makes rainfall and planets orbit, just applied at a different scale. A scale of millions to billions of solar masses. And at that scale, The consequences are objects that outshine galaxies. The universe doesn't build them, reluctantly or rarely. At cosmic noon, when the conditions were right, they were everywhere. The sky in the early universe, if you had been there to observe it, would have been populated with blazing engines. Not the relatively quiet, settled universe we see today. A young universe full of galaxies in the process of forming, merging, and feeding massive black holes. A violent and productive era that ultimately shaped everything that came after, including us, including the Milky Way, which bears the scars of its own past activity in the structure of its central region and the chemistry of its bulge, including every galaxy you can see in the night sky, each of which has a dormant black hole at its center that once, billions of years ago, was far less dormant. The Quasar era is over, but its products are everywhere, written into the structure of every large galaxy, encoded in the mass of every supermassive black hole, preserved in the temperature of the intergalactic gas, visible in the radio lobe, fossils still glowing in galaxy clusters, and arriving as light, still, from the distant past. We live surrounded by the aftermath of the most productive era the universe has known. And it all began with hydrogen, and gravity, and time. There is a particular piece of light that has been traveling for a very long time. It left its source when the universe was less than 2 billion years old, before Earth existed, before the Sun existed, before the Milky Way had finished forming. It traveled through expanding space for over 12 billion years, dodging nothing, losing energy steadily to the expansion of the universe, redshifting toward longer wavelengths. And then, somewhere between 1 and 3 seconds ago, depending on where you're sitting, that light entered a telescope. A CCD chip converted it to electrons. Electrons became data. Data became an image. And in that image, among the other faint smudges and points, one particular point of light is a quasar. A quasar from a time when the universe was young and violent and making the decisions that would shape everything that came later. That light doesn't know anything about the 12 billion years it spent crossing space. It doesn't know that the galaxy that produced it has long since run out of fuel and grown quiet. It doesn't know that the black hole at its center, billions of solar masses of compressed space-time, is probably still there, dormant now, waiting for gas that may never come. The light just arrived, and we received it. Think about what it actually means to hold that fact in your head. You are looking at the past. Not metaphorically. Not approximately. You are receiving photons that were emitted before the solar system existed. The event that produced those photons, a black hole consuming hundreds of solar masses of gas per year and releasing more energy per second than the entire Milky Way, is over. Has been over for longer than Earth has existed. And yet here you are, in the present, receiving its light. The universe has a built-in delay. Nothing you observe at cosmological distances is happening now. Everything you see is a record of the past. And what that record shows is a universe that was once populated by these engines of unimaginable power. That is gone now. Or rather, it is finished. The engines haven't disappeared. They're still there, at the centers of galaxies. Every large galaxy, including ours. Every galaxy you've ever seen in a photograph of the night sky. They're just quiet now, running on fumes. The Milky Way's central black hole, Sagittarius A, 4 million solar masses, is consuming gas at a rate 1,000,000 times lower than it would need to shine as a quasar. The difference between what Sagittarius A is doing now and what a quasar does is not a matter of type. It's a matter of appetite. Give Sagittarius A a large cloud of gas, an angular momentum, and a few 100,000 years, and it would shine. Not as brightly as the most luminous quasars, which are powered by black holes 10,000 times more massive, but bright. More than bright enough to be detected across the observable universe. What stopped it? The quasar stopped itself. When the central engine was active, the energy it released was so intense that it blew away the gas supply. The feedback loop we discussed earlier. The quasar fed, grew, heated, and expelled the gas that fed it, and in doing so, extinguished its own food supply. And then it went quiet, and stayed quiet. We live in the aftermath of that quieting. A universe of galaxies with dormant black holes at their centers. Old black holes that once burned brightly and are now still. Fossils of a more violent era. The radio lobes, the millions of light-year-long structures left by ancient jets, glowing still. The Fermi bubbles, extending above and below the Milky Way's plane, still detectable today. Relics of whatever our own galaxy's central engine was doing millions of years ago, when it was marginally more active than it is now. We live among the aftermath. The scars are everywhere if you know how to look. And here is what that means for you specifically. Not in a vague, inspirational sense. In a precise, physical sense. The heavy elements in your body were forged in stars. That much is well known. The iron in your blood. The calcium in your bones. The oxygen in every breath you take. Stellar nucleosynthesis, supernovae, the whole chain from hydrogen to the periodic table. But the environment in which stars could form, the environment in which galaxies could stabilize into the long-lived structured things they are today, was shaped by the quasar era. The gas that didn't get blown out of galaxies by quasar winds. The cooling curves of intergalactic gas modified by quasar heating. The chemical enrichment of the circumgalactic medium by outflows. The correlation between black hole mass and galaxy mass that implies a co-regulation, a mutual growth that terminated at roughly the right time to produce galaxies like ours. All of these processes, running over billions of years, produced the Milky Way as it is now. A galaxy old enough, stable enough, metal-rich enough, structured enough to form a solar system with rocky planets at the right distances from a stable star. The quasar era is not separate from your existence. It is part of the causal chain that produced it. Without the quasar era happening when and how it did, the subsequent evolution of galaxies is different. Perhaps very different. Whether a planet like Earth could form in a galaxy whose evolution was substantially altered is not something we can calculate precisely. The counterfactuals are too complex. But the chain is real. The quasar era is part of the backstory of your existence. Written many chapters back. Easy to miss if you're only reading the recent pages. There is also something deeply strange about the scale of what we've been discussing. You are thinking about objects that contain the mass of billions of suns compressed inside a region smaller than the solar system. You are thinking about disks of plasma reaching temperatures of tens of millions of degrees, releasing more energy per second than 1 trillion stars. You are thinking about jets of plasma extending for millions of light years, carrying more power than the combined output of hundreds of galaxies. And the mechanism that drives all of it is, at its heart, simple. Things fall. That's it. Gravity makes things fall. Material falls toward a massive object. The falling releases energy. The energy is enormous because gravity is deep and because angular momentum forces material into a slow spiral rather than a direct plunge. The physics is not exotic. There is no unknown force operating here. No undiscovered particle. No speculative extension of the standard model. Just gravity, angular momentum, magnetic fields, and plasma physics. Known quantities. Known interactions. Applied at a scale and in a configuration that produces results that strain every intuition you've developed about what the universe is allowed to do. The universe is allowed to do this. It does it routinely. It did it billions of times, billions of years ago. It created the most luminous objects that exist or have ever existed, using only the laws of physics that also govern the falling of a dropped pen. If that doesn't unsettle you slightly, you haven't thought about it long enough. The numbers don't stop being staggering just because we've assigned them names. 500 trillion solar luminosities, 17 billion solar masses in a single black hole, 370 solar masses of gas consumed every year, plasma jets stretching for 16 million light years, a quasar era lasting 2 billion years, during which essentially every large galaxy in the universe was, briefly, among the most luminous things in the cosmos. These numbers are the real universe, not metaphors, not approximations. The actual quantities describing actual objects made of actual matter following actual physics. And the physics, right down to the elegant equations of general relativity and magnetohydrodynamics, is beautiful in the way that precise things are beautiful. Not sentimental beauty, not comfortable beauty. The beauty of a thing that is precisely what it is, exactly as extreme as it has to be. No more and no less. A quasar is what happens when enough mass occupies a small enough space and enough gas falls toward it at the right rate. And the universe, by the nature of how gravity assembles structure from the quantum fluctuations of the inflationary epoch, reliably produces that situation. Billions of times. In the youth of every large galaxy that has ever existed. You are living in the old age of a universe that was once very young. And in its youth, it burned differently. Not with the gentle, steady glow of a middle-aged galaxy, but with the furious, unsustainable brilliance of something consuming itself to make light. The quasar era is over, but the light from it is still arriving. It has been arriving your entire life. It was arriving before you were born. It will arrive long after every living thing on this planet is gone. Some of it is arriving right now, as you watch this. Patient photons from a time before the Earth existed, crossing 12 billion light-years to land on a mirror or a sensor in a desert in Chile or in orbit above the atmosphere, and be recorded. The universe is telling us its history, and we are only just beginning to be good enough listeners to understand what it's saying. Go outside tonight. If there's no cloud cover, look up. Not at anything in particular, just at the dark space between the visible stars. In that darkness, if you had a large enough telescope, you would find quasars. Thousands of them, in every direction. Each one a window into the past. Each one a record of the era. when the universe was young and the black holes at the centers of galaxies hadn't yet eaten themselves quiet. They're there, in the dark, waiting to be found. Still arriving after 12 billion years of travel. The universe doesn't announce itself. It just sends the light. That is what a quasar really is. And the fact that it exists at all, the fact that the physics that governs our ordinary world produces objects of this scale and power as a routine consequence of gravity and angular momentum, is something worth carrying with you. We are not in a small, quiet universe. We are in a universe that builds engines of 100,000 galaxies worth of luminosity and scatters them across the sky by the millions. By the millions. And we are the things that learn to read what those engines are saying. Barely. But learning. Good night.